Very good afternoon. Let us see about the next part of the lanthanides and the actinides, which are the F block elements. The elements constituting the F block are those in which the 4f and 5f orbital progressively filled. These elements are the member of group 3. The F block elements are also termed as inner transition series. It is because, literally speaking, they constitute transition series within transition series, that is the D block elements. In addition to incomplete D subshell, their F subshell is also incomplete. There are 7 F orbitals in a given shell. As much as 14 electrons can be occupied in a given F block series. The general electronic configuration of F block elements is, that's what, N-2 F1 to 14, N-1 D0 to 1 and Ns2. Lanthanide series, that is the xenon, which is neutral element, 4f1 to 14, 5d0 to 1 and 6s2 is the normal electronic configuration or general electronic configuration. And actinide series, which is of having Rn radon 4f1 to 14, 6d0 to 1 and 7s2. So this is the incomplete D subshell as well as the F subshell. Lanthanide series, as shown on the slide, see that atomic number 57 and the next 14 elements atomic number 58 to 71, these elements are placed in a lanthanide series or named as a lanthanones. Actinoids are 89 atomic number and the next 15 elements to lawrencium, that is the actinide series elements. The name lanthanide has been derived from lanthanum, which is the prototype of lanthanide. These elements are placed in the 6th period of the periodic table. Originally, these elements have term as rare earths. It is because for many years pure compounds of these elements were difficult to obtain, and nowadays the term rare earth is avoided because many of these elements are far from rare. 5 A block elements, second inner transition series, actinides or actinones. In these elements, differentiating electron goes to 5f orbital. This series includes 15 elements from actinium, atomic number 89, to lawrencium, atomic number 103. The name actinide is derived from actinium and the very first member of the series. Why A block elements placed outside separately? It is interesting to note that the A block elements, lanthanides and actinides, are placed outside the body of the periodic table. The reason for this is the remarkable similarities among the chemical properties of the lanthanides and also among the various members of the actinides. The similarities in properties in turn is due to the similar electronic configuration of the outermost shell. These elements differ only in the number of F electrons which do not take part in chemical bonding. Difference from D block element in which differentiating D electrons are involved in chemical interaction. Let us see the characteristic of lanthanides. Although the lanthanum 57 atomic number and the following elements up to the lutetium 71 resemble each other in their properties, lanthanum itself is studied in D block elements and not A block. It is because here F orbital has no electron. The F orbital actually starts from the cerium atomic number 58 and is completely filled at lutetium atomic number 71, and hence elements from cerium to lutetium are actually grouped as 4A block elements. Further, since these 14 elements follow lanthanum, these are also termed as lanthanides or lanthanones. The electronic configuration represented as xenon 4Fn plus 1 5d0 6s2 or xenon 4Fn 5d1 6s2. The valential electronic configuration is 4f 1 to 14 6s2. Oxidation states. The lanthanides too display variable oxidation state but much less than those displayed by the transition elements. The characteristic and the most oxidation stable state of the lanthanides is +3 Ln3 plus. The atomic and the ionic radii. Steady decrease in the size of atoms and ions with the increasing in atomic number as we move across from lanthanum to lutetium is called lanthanide contraction. Thus, among lanthanides, lanthanum has the largest and the lutetium has the smallest radius. It is caused by poor shielding effect of the 4f electrons which is inner. As atomic number increases, the positive charge increases by +1 unit and one more electron enters in the same subshell. The extent of shielding for electron is less in 4f subshell as compared to the electron in d subshell, which is shown as a graphical manner on the right side of the slide. So this is about the atomic radius. The contraction which is shown as a graphical manner, that is the inside the nucleus, which is of having outermost that penultimate shell, ns orbital valence shell, n-2f orbital, that antipenultimate shell, last coming up electrons enter in this orbital, actually which is inner side, or it is the near to the nucleus, and outer side which we have that ns orbital which is valence shell. So as much as the atomic number increases, the electron enters to the antipenultimate shell, and that's what it loads or it contracts with the valence shell, and that's what that there is the shielding or the contraction which it happens. So that last coming electron enters in this orbital which is far from valence shell. Due to this, shielding effect doesn't work and attraction effect of nucleus works, whereby atom gets contracted, and that's what outermost shell stretched more towards the nucleus, and electron which is entered in an antipenultimate shell, that's what the contraction it happens as the atomic number increased. Among the lanthanides, the consequences which it happens, they are the basicity of ions decreases from lanthanum to the lutetium. So their oxides and hydroxides are less basic. As the atomic size decreases across the series of the elements, following lanthanides show change in their physical properties. So the size decreases, the ionization potential increases, metallic nature decreases, electropositivity decreases, electronegativity increases, and tendency to form the complexes which is also increases as the series it is to be going on with the atomic number. Post lanthanides, occurrence of elements as pairs due to similar size of 4D and a 5D in a group, they have similar physical and chemical properties. They occur together in nature and their separation becomes very difficult. The zirconium, hafnium, nebulium, tantalum, molybdenum, tungsten, likewise the examples are there. The densities, 5D elements have very high densities as down the group there is large increase in mass but no increase in volume. And occurrence of the yttrium along with heavier lanthanides, yttrium has similar charge and size to holmium 3 plus and erbium 3 plus, hence it occurs with, and that's what the separation of it becomes somewhat difficult. The color due to the FF transition, the lanthanide metals are silvery white. The trivalent lanthanide ions are colored both in the solid state and in aqueous solution. The colors are unchanged even on alteration of the anions, indicating that they are characteristic of the cations. The approximate color of the lanthanide ions in aqueous solution in +2 solution, +2 oxidation state, +3 oxidation state, and the +4 oxidation state, where that the color of these ions it is to be shown. The magnetic properties, lanthanum 3 plus, whereas it has the 4f0 electrons, and the lutetium 3 plus, which has the 4f14 electrons having no unpaired electrons, and these do not show paramagnetism, while all other tripositive ions of lanthanides are paramagnetic as they are having that unpaired electron. The complexes, although the lanthanide ions have high charge plus 3, their large size 0.85 to 1.03 angstrom imparts them low charge density charge to size ratio, with the result they cannot cause much polarization and hence do not have much tendency to form complexes. Their complexes with unidentate ligands like beta diketones, oximes, and ethylene diamine tetraacetate are fairly common. Occurrence and separation of the lanthanides. Cerium is the 26th most abundant element in the earth crust. Neodymium is more abundant than gold, and even thulium, the least common naturally occurring lanthanide, which is more abundant than iodine. Cerium, earth and light earth, atomic number 57 to 63. Yttrium, earth and heavy earth crust, atomic number 64 to 71. Lanthanide minerals, monazite, bastosite, exenite, gadolinite, xenotime, etc. These minerals found in Sweden, Norway, Brazil, Australia, Texas, Florida, and Canada. The ion exchange lanthanum 3 plus are strongly adsorbed by cation exchange resin. This is the chelating agent which is used for these purposes. So ion can be exchanged for the separation of the lanthanides. This method is a synthetic ion exchange resin with functional group like COOH and SO3H, which is packed in a long column fixed in a vertical position. The steady decrease in size and consequent decreases in basicity causes the steady increase the complexing ability with increasing atomic number of lanthanides. When an aqueous solution containing the mixture of trivalent lanthanide ions M3 plus aqueous, which is passed through a column having synthetic cation exchange resin solid, the M3 ions replace H plus ions of the resin and thus get fixed on that. And that's what reverse order of the series which is bounded first. So the atomic number which is of larger, it is bounded first. The reaction it is M3 plus 3HR, R is the resin. There is the formation of the bonding with metal and the resin solid, and 3H plus ions which is released due to the M3 plus oxidation state of the ions. Another method of the separation it is the solvent extraction, first reported by the Fischer, based on different insolubility of lanthanum salt in water and organic salt tri-N-butyl phosphate (TBP). Ln3 plus aqueous is extracted in continuous counter current process into a non-polar organic liquid, that is kerosenes. Ln3 plus 3NO3 aqueous and 3 TBP, which is in organic phase. There is the reaction which is to be formed by and extraction LnNO3 thrice TBP thrice organic complex which is to be formed. The separation of the lanthanides in ion exchange method is based on basicity of the hydroxide, size of the hydride ions, size of the unhydrated ion, and the solubility of their nitrate. Uses of lanthanoids. Lanthanides used to the production of alloy steels for plates and pipes. Example, mixed metal which consists of lanthanide metal 95% and iron 5% and traces of sulfur, carbon, calcium and iron. Aluminum. Mixed metal is used in magnesium based alloy to produce bullets, shell and lighter internal. Mixed oxides of lanthanoids are exploited as a catalyst in petroleum cracking. Some individual lanthanum oxides are used as a phosphorus in television screens and similar forecasting surfaces. Because of their paramagnetic and ferromagnetic character, their compounds are used in making magnetic and electronic devices. Ferric sulfate is an oxidizing agent in volumetric analysis. The characteristic of actinoids. Actinoids. The actinoid include the 14 elements from thorium to the lawrencium. The actinoids are radioactive elements and the earlier members have relatively long half-life. The latter ones have half-life values ranging from a day to 3 minutes for lawrencium, whose atomic number is 103. The electronic configuration. All the actinoids are believed to have electronic configuration 7s2 and variable occupancy of the 5f and 6d subshell. The 14 electrons are formally added to the 4f through, though not in thorium, whose atomic number is 19. From Pa onwards, the pi f orbitals are complete at element 103. The irregularities in the electronic configuration of the actinide, like those in the lanthanides, are related to the stabilities of the F0, F7 and F14, that is zero stability, half field stability and complete field stability occupancies of the pi f orbital. Thus the configuration of americium and the curium are radon 4f7s2 and radon 5f7 6d1 7s2. As you are to be seeing the table which is of giving that the atomic number of the actinide series elements. The atomic and the ionic radii, which is similar, showing as like a lanthanodes. Due to the contraction, the general trend in the lanthanide is observable in the actinide as well. There is a gradual decrease in 3 plus in the size of the atoms or M ions across the series. This may be referred to as the actinide contraction, like lanthanide. The contraction is, however, greater from elements to an element in the series, resulting from poor shielding by 5f electrons. Oxidation state. There is a greater range of oxidation state, which is in part attributed to the fact that 5f, 6d and 7s levels are of comparable energies. The actinides show in general 3 plus oxidation state. The elements in the rest half to the series frequently exhibit higher oxidation state. The maximum oxidation state increases from plus 4 in thorium to plus 5, plus 6, plus 7 respectively in palladium, uranium and Np, but decreases succeedingly elements. The actinoids resemble the lanthanoids in having more compounds in plus 3 state than in plus 4 state. However, plus 3 and plus 4 ions tend to hydrolyze. Uses of actinoids. Thorium used in atomic reactors and in the treatment of cancer. Its salts are used in making incandescent gas mantles. Uranium is used as a nuclear fuel. Its salts are used in glass industry for imparting green color, textile industry, ceramic industry, and in medicines. Plutonium, it is used as a fuel for atomic reactors as well as for making atomic bonds. Thank you. Put notes on your notebook, practice regularly, stay safe, study hard, and if you have any difficulty, please mail me. Thank you. Thank you very much.